Now today we are going to start our discussion on coordination compounds. It is part second. Today we are going to discuss some another aspects on coordination compounds. For example, isomerism. It is an important property that is shown by the coordination compounds as we change our compound to compound. What are isomers? The first question arises, what are isomers? Isomers क्या होते हैं? Compounds having same composition but different arrangement of atoms either through bonding or through arrangement of atoms in space. That is, they have same molecular formula but different structural formula. Different structural formula means their coordinating tendencies or their ionizing tendencies may be different with respect to each other. This property of these compounds may vary a lot due to this unique feature. It is a unique feature that can affect the various properties of coordination compounds. There are various types of isomerism observed in different types of coordination compounds. On a broad way, we can separate out these types of isomerism into two parts. First, structural isomerism, and second, stereoisomerism. These depends upon the basic properties of isomerism. For example, if we are discussing about isomers and we are showing that we have same formula but they are different structures, on this, on a broad way, we can separate out these isomers into two types. First one, that is structural isomers. Second is stereoisomers. Structural isomers are those in which the bonding nature, the coordination behavior are different of a metal with the coordinating ligands. This structural isomerism can be separated out in four parts, broadly on two parts. First is coordination isomerism, second is linkage isomerism. Hydration and ionization isomerism also observed on the structural isomerism base. Now the stereoisomers, which have same bond, different spatial arrangement around the central metal atom. A central metal atom can accommodate different types of ligands in different ways. First of all, we discuss about coordination isomerism. What is coordination isomerism? As its name suggests, that there is some difference in the coordination behavior of a ligand with the central metal atom. The isomerism due to difference in the bonding of a ligand that is bonded to the metal. The composition of the complex ion varies according to their coordination with the ligand. For example, we will discuss here cobalt pentamine chloride, in which the chloride can be bound inside the coordinating sphere or outside the coordinating sphere. Here in this example, if chloride and bromide can interchange their places within the coordinating sphere and one can rest outside the coordinating sphere, and only this change in the compound can change the entire property of the complex. Next example is of chromium hexa-aqua complex. This chromium hexa-aqua complex is violet in color, in which 3 chlorides remains outside the coordinating sphere, whereas if 5 aqua complex containing 1 chloride and 2 chlorides remain outside the coordinating sphere, due to this interconversion of ligands, that is of chloride and aqua, interchange with each other. This interchange can change its property in a broader range. For example, this hexa-aqua complex of chromium is violet in color, whereas this penta-aqua complex of this chromium is of green in color. This is the major change that we can observe from our visible eyes, that is of color. And here we are getting a change in the color and we are observing it directly from the naked eye. So a coordination isomerism may affect on its important property. Now the linkage isomerism, it is due to the bonding of a ligand through different atoms with the metal. Different atoms means if a ligand consists of one or more atoms, then it can bind to the central metal atom through different ways. For example, here pentamine cobalt, which is attached with the oxygen in this complex, and in another example, pentamine cobalt can be connected with the nitrogen. The molecule or the ligand remains same, that is NO2, but the coordinating sites with the central metal atom is different in both the cases. In first case, cobalt is coordinating through oxygen, where in second case, cobalt coordinated through nitrogen. And this coordination, this linkage, which is prominency through the properties, that is orange in color, the first one example, and the second example is red in color. So this is the prominent example that we can see there is a direct change in color with the linkage or either the coordination of ligand with the central metal atom. Now the hydrate and ionization isomerism. In hydrate isomerism, it depends upon the position of water that is attached to the central metal atom, whether it is inside the sphere or outside the sphere. But the number of water molecule attached to the coordinating sphere will remain different in both the cases. In case of hydration isomerism, whereas in ionization isomerism, it constitutes from the type of ions that ionizes from two similar molecules. For example, if there is one chlorine outside the coordinating sphere and two chlorine inside the coordinating sphere, then if we dissolve this compound, we will get only one chloride that is outside the coordinating sphere in the form of ions. The next example, if two chloride ions are outside the coordinating sphere, then on dissolving into water, it will give two chloride ions. And for this chloride detection, we can use a chloride test, and from the consumption of chloride molecule, that is 2 in case of second and 1 in case of first, we can easily assume that there is some ionization isomerism exists in both the compounds. Now come to the point of geometrical isomerism. What are geometrical isomers? In which there is a different spatial arrangement of ligands, means the spatial arrangement around the central metal atom is different in case of geometrical isomerism. If both like groups are on the same side, then this is called as cis isomer. If both the same groups are on opposite side, then it is called as trans isomers. These can have different chemical and physical properties depending upon their cis and trans nature. For example, diamine dichloroplatinum. If both the chloride and both the amine molecules at the same side, then these are called cis complex. Whereas if amine and chloride are on the opposite directions, then they are called trans isomers of this complex. Similarly, cobalt tetraammonium, in which 4 amine directly attached with the cobalt and 2 chlorides are directly attached with the cobalt, but their positions can interchange with each other, like this. Here in cis and trans isomerism, the coordination number of 4, okay, that may adopt the geometry of tetrahedral or square planar. The tetrahedral does not show any cis and trans isomers, whereas the square planar only shows geometrical isomerism of cis and trans. Here the Ma2B2, Ma2BC, these two types of molecules on square planar can show only the cis and trans isomers. Here in this case, platinum is the central metal atom and 2 ammonia molecules are on the opposite side, whereas two chloride molecules are also on the opposite side. This is called trans isomers, where the similar group like ammonia or chloride are on the opposite side. That's why it is called as trans isomers. Whereas in case of cis isomer, the two ammonia molecules are on the same side. That's why it is called cis. Also, chloride is on the same side. That's why it is called cis isomer. It may be possible that these two chloride ions can be interchanged with other type of molecules or ligands, that is M2A2BC type of complex, in which M is platinum and A is ammonia or chloride, and the other two neutral ligand or anionic ligand may get changed with another type of ligands that can be of similar nature or same nature. Now for the coordination number 6, that can adopt octahedral geometry and can show geometrical isomerism in the same way, like an A4B2 type. A4B2 type means 4 ligands of A type and 2 ligands of B type, which can also be changed from A4 to BC. A4 means 4 A type molecule or ligands can directly attach with the central metal atom, and 2 different BC ligands can be attached with the central metal atom. Here A2 and B2. A2 means it is a bidentate ligand. It is a bidentate ligand and 2 bidentate ligands are present. That's why it can occupy its 4 position, and 2 another position of octahedral sites are occupied by other monodentate ligand, that is B2 type. Similarly, these 2 B2 type ligands can be interchanged with the BC type of ligands. These type of molecules will show cis and trans isomers, in which there is a central metal atom. In this case it is cobalt, and the 4 A4 type molecules are ammonia, NH3, NH3, NH3 and 4 NH3. These 4 NH3s are on the planar side, whereas these 2 chloride ions remains on the opposite directions. This is called trans isomers, in which the similar type of same type of molecules remains at the opposite end. In this case, here 4 ammonia molecules are present here, 3 at the planar side and 1 at the bottom or top position, whereas 1 chloride and 1 chloride at the planar side will face each other. That's why they are called as cis isomer of coordination number 6. Now coming to stereoisomers, in which is observed. In this case, the any compound changes towards the plane polarized light, which may be of opposite nature. If it rotates the plane polarized light through right side in the direction, it is called as dextrorotatory. If it is rotating this plane polarized light into left side, then it is called as liborotatory. The isomers that are non-superimposable with each other are called enantiomers. For example, this molecule has a non-superimposable mirror image, then it is called as enantiomer. The enantiomer, the important property of the enantiomer is that it does not contain a plane of symmetry, and these type of molecules are particularly called as chiral molecules. The chiral molecules are those which does not contain any plane of symmetry, so that we can have their isomers of such type that can't be superimposed with on its mirror image, and those are called enantiomers. There are certain properties of enantiomers on the basis of which we can identify, yeah, separate out both the compounds or both the isomers of the same compound. Means the similar properties, that is solubility. Both the isomers can have same solubility, same melting point, same boiling point, or it may have same color or same chemical reactivity it can show, but it is a different property that can interact with the plane polarized light in a opposite manner. Means it may be of D nature or it may be of L nature. It can rotate the plane polarized light into right side or it can rotate plane polarized light into left side. Here in this example, this is isomer 1 and this is isomer 2, in which one is dextrorotatory and another is levorotatory. These two isomers are non-superimposed with each other, means they are called enantiomers, and this particular type of molecules are called chiral molecules. One of the important aspects of coordination compounds are effective atomic number. What are effective atomic number? It depends upon the stability of a complex compound. What configuration, what particular type of configuration a coordinating compound is attaining, so that we can call it as a stable compound. The stability of complex compound that was explained on the basis of effective atomic number, and in most of the complex ions that becomes equal to the atomic number of the next inert gas. Means if central metal atom attaining a certain configuration, then it must or it may coincide with the next inert gas atomic number. It is the sum of the electrons present in the metal ion and the total number of electrons donated by the ligand. In coordination sphere, we have two types of molecules or ions. First is metal ion, second is ligand, that may be a neutral or a anion. So the effective atomic number, it is the sum of the electrons that is present in the central metal ion plus the electron pair donated by ligands. The sum of these two types of atoms or ions electronic configurations, that consist of effective atomic number, and that may be equal to the next atomic inert gas. The effective atomic number, that is equal to the atomic number of metal minus its oxidation state. Minus its oxidation state means if a compound contains 26 electrons in its orbital, then and 3 is the oxidation state, then the originally in the form of a complex it contains only 23 metal electrons, and plus the total number of electrons donated by the ligand. It means how many electrons a ligand donating to the central metal atom. That consists of a effective atomic number, means EAN. Now there are some data on this concept of EAN. Here, if we consider hexacyanoferrate, then the central metal atom is iron. Its atomic number is 6 and its oxidation state is 2. So the effective atomic number, here the number of electrons donated by ligand, by the 6 cyanide ligands. One cyanide contains one bond pair, means 2 electrons, means total 12 electrons donated by the ligands to the central metal atom. Here the effective atomic number calculated is 26, that is central metal atom number minus its oxidation state plus the number of electrons donated by the ligand to the central metal atom. That becomes equal to 36, and that is equal to the inert gas atomic number. And each complex tries to attain that inert gas atomic number so that it can attain a maximum stability, so that it can't be get reacted with another compound. Now the next example of tetracyanocuprate. Here in tetracyano-copper compound, 29 is the atomic number of copper, and oxidation state of the central metal atom is +1. The total 4 cyanide molecule give 8 electrons to the central metal atom. Here on calculation we get 36 effective atomic number, which is same as that of inert gas, next inert gas atomic number. There are certain exceptions in which we have less than or more than that of next inert gas atomic number. For example, hexaamino chromium complex, in which chromium is the central metal atom and it contains 24 atomic numbers, whereas +3 is the oxidation state of chromium in this particular compound. The total number of electrons donated by the 6 amino molecule is 12. On calculating, 24 central metal atom minus 3 its oxidation state plus 12 the number of electrons donated by ligand to the central metal atom, and it becomes 33, which is less than that of inert gas atomic number. And this less than that of atomic gas number may further start its reactions with another compound, so its stability becomes less than that of its corresponding compounds. Here there are certain examples from which we can say that in maximum cases the effective atomic number may reaches to its next inert atomic gas number, so that the molecule or the compound can, or the complex can attain the stability like that of inert gas. Now the properties of coordination compounds. Mainly there are 3 properties that are of useful nature in coordinating compounds. First is color, and second is magnetic properties, and third is catalytic properties that prominently can be covered in the coordination compound chapter. There are certain various properties that we can cover, but due to the limitation of time we only cover here the color, magnetic properties and the catalytic property of the coordination compounds. First, color in coordination compound. Here the spectra arises from the electronic transition between the T2G and the EG set of molecular orbitals. That is, the absorption of light occurs when electrons are promoted from lower to higher energy states. Here it is important to know how the d orbitals of the transition series or the coordinating compound metals splits into 2 parts. Here it is the d orbital of the central metal atom, and when it is gets coordinating with the ligands, then it can split into 2 parts, that is T2G and EG. T2G contains 3 d orbitals, whereas EG contains 2 d orbitals. This bifurcation is based upon their orientation of d orbitals around the central metal atom. The orientation of these 2 types of orbitals, the T2G oriented itself in between the axis, whereas these EG orbital set, these are directed towards the axis. That's why when a ligand approaches to the d orbital, that ligand bifurcate these 2 sets of these orbitals into two sets, that is EG and T2G, and the difference between the energy of these 2, the value of delta for the complex, are used to determine the UV visible spectra, what color we will get on transferring an electron from T2G to EG orbital. The energy gap, that is delta, is referred to the crystal field splitting energy. This crystal field splitting energy further determines the color of the complex. Now the color of the complex depends solely upon the magnitude of crystal field splitting energy. There are two types of species present in a coordinating compound. One is metal and another is ligand. First we will discuss about the metal. The larger the metal, the larger the splitting energy or delta. Here higher the oxidation state, the larger will be the splitting of the energy. Here in the second case, ligand, the spectrochemical series depends upon the type of nature of ligand. What type of ligand we are using for coordinating compound. If weak field ligand is available, then low electrostatic interaction, small crystal field energy, whereas for high field ligand, high electrostatic interaction and large crystal field energy. The another aspect or another property that we should discuss here is the catalytic properties. What are catalysts? The capable of forming an unstable intermediate compound which readily decomposes, yielding the desired product and separate out itself in original form. It is called as catalyst, in which A and B are two reactants which are reacted in presence of a catalyst, which will give A dot B dot catalyst, which is an intermediate, which gives out C is the product plus catalyst. The conclusion of this reaction is that catalyst take part in the reaction and gets outside after completion of reaction in its original form. The coordination compounds show its catalytic property due to its variable state. Due to variable oxidation states, they are good catalytic activity because from reactant state they can adopt one type of oxidation state. In intermediate state they can go through a different type of oxidation state that can be changeable, and from this that can get, when the reactants gets converted into product, again the catalyst obtained its original oxidation state and gets separated out. The next property are the magnetic properties of coordination complexes. It is due to the presence of unpaired electrons. The magnetic properties in all the transition metals or general metals, the unpaired electrons are the sole factor to determine their magnetic properties. That is why it is because the magnetic field of an electron interacts with the external magnetic field, and it induces that particular metal in the magnetic field to get attracted into the magnetic field or gets repelled from the magnetic field. If there are number of unpaired electrons present, then the magnetic field of those electrons get interacted with the external magnetic field, and the unpaired electron containing metals are called paramagnetic in nature, and this paramagnetic character is attracted by the external magnetic field. The nature of the ligand also creates impact on the nature of splitting of the metal d orbitals, which in turn decide the pairing of the electron. The magnetic field also gives the magnetic moment. That magnetic moment is given by the mu s is equal to under root 2 n plus 1. For example, it has cobalt hexaamino complex and cobalt hexafluoride complex. In hexamino complex, it is diamagnetic in nature, whereas the cobalt hexafluoride is the paramagnetic in nature. It is due to the factor that the amine complex, amine ligand in particular complex, amine gets paired the unpaired electrons due to its larger splitting value, whereas the fluoride can't pair up the unpaired electrons in particular compound. That's why due to the pairing factor it is diamagnetic in nature, and due to the unpaired electron unpair factor it is paramagnetic in nature because it contains some unpaired electrons which can interact with the external magnetic field. A crystal field splitting of d orbitals in high and low spin situation for a d5 metal. How we can define these type of values? Here there are two set of d orbitals, Eg and T2g. In case of larger splitting, that is case of ammonia, ammonia creates larger splitting and which can pair up the electron here. Due to this pairing, the net spin becomes zero, which makes the compound dimagnetic. Whereas in case of fluoride ion, there is a small splitting observed in case of fluoride ion, which can give a high spin complex. High spin means there are certain unpaired electrons remain in the outermost orbital, d orbital. So the net spin becomes 5, and this makes this compound a paramagnetic in nature, in which the unpaired electron can interact with the external magnetic field, making it magnetic environment. What are high spin and low spin complexes? If we assume the electronic configuration of metal ion, S electrons are lost first. In case of titanium, we have D1 configuration. In case of vanadium, we have D2 configuration. In case of chromium 3, we have 3 electrons in outermost d orbital. So what Hund's rule says? It says first 3 electrons are in separate d orbital with 3 spin parallel. Here it is 3 unpaired electrons present in the T2g orbital. Whereas in case of low spin, if the splitting value is more, then electron would like to prefer and to get accommodate in the lower energy orbital with T2g electrons. Here in case of high spin, each electron will accommodate its separate orbitals and will remain unpaired. The fourth electron has choice. Higher orbital, if delta is small, means it creates small splitting, means it will be higher in spin. Whereas lower orbital, if delta is large, means the fourth electron will accommodate the lower orbital and it will become low spin. For a weak field ligand, a small splitting, a small delta creates high spin complexes, whereas for the strong field ligands, larger delta creates low spin complexes. High spin and low spin we can also understand in terms of number of unpaired electrons present in the d orbital. If we have 5 unpaired electron in d orbital and 4 unpaired electron in d orbital, means the 5 unpaired electron in d orbital are high spin complex, and the 4 unpaired electron in d orbital we have low spin complexes. And what are inner orbital and outer orbital complexes? It is the complexes which involve inner d orbital for the bonding purpose or for the coordination bond are called inner orbital complex, in which 3d orbital involvement is placed. In case of inner d orbital, the configuration attained by the central metal atom would be n-1 d1 to 10, n-n ns 1 to 2 configuration that would be attained for the inner d orbital compounds. What are outer orbital complexes? Outer orbital complexes are those in which the d orbitals are of outside the s orbital, means which involves outer d orbital are called inner orbital complex. For example, 4d and 5d orbitals are outer orbital, than the S1, 4s1. It means the orbital involvement is important in case of d orbital. If it is of 3D, then it is called inner orbital complex, and 4D and 5D generally form outer orbital complexes because 4D and 5D orbitals are outsider than that of s orbital. In case of outer orbital complexes, we have configuration of n-1, s1 to 2 and nd 1 to 10 configuration of this type. Now the last aspect of this coordination compound are the geometries that can be attained by the complexes. It depends or solely depends on the number of coordinating ligands. The number of coordinating ligands, if we have 2, then there should be a linear geometry around the central metal atom. For example, silver diammonia complex. In case of coordination number 4, 2 types of geometries can be attained, a tetrahedral or the square planar, depending upon the nature of ligand and also depending upon the approach of ligand towards the central metal atom. If octahedral complexes ligands are approaching towards the axis, then it can form square panel complexes, and if ligands are approaching to the central metal atom in between the axes, then it can form a tetrahedral complexes. In case of 6 coordination number, 6 ligands approach to the central metal atom in the form of octahedral, then the geometry would be of octahedral type. If the ligands are of that nature that it can split the d orbital into a broader way, then the chances of forming of square planar complex is more than that of octahedral complexes. So in this chapter we have covered almost all of the properties of coordinating compounds, but due to lack of time we can conclude it here. Thank you very much.